Okay, we're about ready to move into part 2 of the network value-added attributes. This time we're going to discuss the analysis attributes, one of which is stream order. So for those of you who are interested in stream order, we'll get to that. Normally, since these presentations are designed to sort of stand alone, we put the fundamentals in all the presentations, but I won't go through those again. Here is a list of the analysis attributes. The names in parentheses are the actual field names in the folder in the DBS. Since they're restricted in terms of their length, they get truncated a little bit, so I included also the larger name for them. We have stream order, and paired with stream order is an attribute called StreamCalc, which has some really interesting applications. We have a LevelPathl identifier, a TerminalPa identifier, and if you remember, I told you there were a lot of identifiers in the value-added attributes. These are all nationally unique. We have the up-level path identifier, down-level path identifier. These are two that we talked about earlier for navigation. We also have Pathlength, arbolet sum, and return divergence. Okay, stream order. The stream order is modeled after Strahler, although Strahler the algorithm only works on a dendritic network, so we had to modify it a bit to make it work with our 60,000 flow splits. But essentially, Strahler says your headwaters are order 1. When two 1s come together, they form an order 2. When two 2s come together, they form an order 3. When two flow lines of different orders come together, the result is just the maximum of those two. So when the 2 and the 1 come together, the downstream stream order is a 2. So what did we do to modify this? The symbols, and I hope you can read them on this, the labels, are divergence, which is the code that tells you whether or not the flow line participates in a divergence, and if it does, whether it's the main path or a secondary path. A slash, then stream order, a slash, and then StreamCalc. So the flow direction in this picture is from the upper left to the lower right. And what we have coming in here is a flow line that doesn't participate in a divergence. It's stream order of 2 and a StreamCalc of 2. But here we are at a divergence, and when we hit a divergence, that's where our algorithm changes from what Strahler would do. Strahler's silent on what to do here. What we do is we propagate the stream order down all the paths. So in this case, stream order 2 goes down both paths. Keep in mind that this is the minor path because its divergence code is a 2. This is the main path, its divergence code is 1. The StreamCalc on the main path retains the same value as the stream order, but the StreamCalc on the minor path goes to 0. And it stays 0 until we come back to the network. So down here, when we've come back to the network, we know we're coming in with a minor branch because the StreamCalc is 0, and we're meeting a main branch because the StreamCalc is equal to the stream order. And so we say we don't want to increase the stream order here, because we would unnecessarily, in a braided system, just start notching up the stream order dramatically. So we keep the stream order of 2, but StreamCalc becomes 2, and we're back to no divergence. And then eventually we have another 2 coming in, and that's when we actually go to a stream order of 3. So stream calculator is always equal to stream order on the main path, or it's 0 on the minor path. And it stays 0 beyond just one flow line. It's not just one flow line. So one of the things that stream calculator can help you do is pull a dendritic network out of the NHD+. If you select all the flow lines where stream order equals stream calculator, you will have a dendritic network. You have just removed all the diversions and their minor paths. So for applications that need what the StreamStats folks call dendrites, it's a really easy, simple query to get one. If you have a model that only deals with a dendritic network, this is the way to get it. Are there any questions about that before we move on? Okay, great. LevelPathl identifier is a unique identifier, nationally unique identifier that follows the stream level. And so the LevelPathl identifier is the unique identifier for, let's say, a stream from the mouth of the stream to the headwaters. Okay, so here we have stream level of 1 going up here, and it has a LevelPathl identifier of 55. Now, we use the hydro sequence number of the most downstream flow line just as a convention as the LevelPathl identifier. So when you're on LevelPathl 55, you can always find the mouth of that LevelPathl by just hunting for the hydroseq that's equal to 55. Okay? We have a TerminalPa identifier as well. And in this case, it's also the hydroseq of the terminal flow line. And so every flow line in this picture has a TerminalPa ID of 55. So whenever you're anywhere upstream of the Mississippi, anywhere in the Mississippi drainage, you'll have a TerminalPa ID of whatever the most downstream flow line is in the Mississippi, and you can jump right to the mouth of the Mississippi by looking for that hydroseq. And using LevelPathl identifier and TerminalPa identifier is really nice. This is the mouth of the Potomac, which is one of my favorite places, since I don't live very far from there. And the hydroseq number is 200004858. And if you select LevelPathl identifier equal to that, you get, whoops, didn't mean to do that. You get the main path. Oh, I guess I did. You get the main path of the Potomac, but it goes clear to the headwaters, and the Potomac name ends along there somewhere, and it becomes, I don't know, the west branch of the Potomac or something. But every LevelPathl identifier goes to a headwater, even if the name doesn't go to a headwater. Okay? If you want to select just the named feature, you can use the GNIS ID to do that. But if you want the entire LevelPathl, you use the LevelPathl identifier. TerminalPa identifier gives you the entire drainage to the mouth of the Potomac. Simple select. TerminalPa equals 200004858. Up and down LevelPathl identifiers are there so that you can know what is immediately upstream and downstream of you. And so they are, in fact, the LevelPathl identifiers of what exactly is upstream and downstream. And they are useful for doing some queries as well. Here is the Potomac, all the tributaries that flow into the Potomac. And the way we found these is we found all the tributaries that had their mouth was upstream of the level path of the Potomac. So now we have all the tributaries of the Potomac. We don't have the Potomac itself, just as tribs. As you can see, VAAs can be pretty handy, even in simple queries. And this is the query that you use to get the level paths of the tributaries, and then you have to actually select everything to get the full tribs. Path length is the distance from the downstream end of the flow line to the network terminus. So if you're in the middle of the Ohio, the path length of the flow line is the distance to the mouth of the Mississippi. Okay? So here's just a picture of path lengths labeled on the flow lines, and you can see that the big values are up at the top of the network, and as you proceed down the network, it gets closer and closer to the terminus, so the path length gets smaller and smaller. Arbolate sum, we talked about that a little bit before. It is used to help us build stream level, is the sum of the length Km, which is the length of each flow line, from the bottom of the current flow line to the headwaters of the entire drainage that drains to that flow line. So it's the total stream kilometers that drain to the bottom of the flow line where you're sitting. Here's another picture, and this is just the opposite of path length. The little numbers are at the top and the big numbers are at the bottom. You can see at the mouth of the Potomac, or whatever this isn't the Potomac anymore, I don't think. It's 16 kilometers of total stream miles flowing to that point. So, yeah. Return divergence is a really interesting attribute. One of the issues one has is you're sitting on the network and somewhere upstream there was a divergence. And you don't know whether that has returned to the network or not. So if you're trying to accumulate attributes down the network and you want to know total upstream values, if it has returned to the network, you'll duplicately count the routed values, okay? So ReturnDiv tells you whether you're sitting in a place where upstream divergence has just come back into the network. And in order to get total upstream accumulation when you're sitting at a place like that, the easiest way is to navigate upstream and just add everything together. Otherwise, all you have to do is add the inflows. Did I lose anybody there? Did I? Okay. You have a divergence, and you don't know when it's coming back. It may come back many, many, many miles downstream. But you want to know when it comes back because you've routed your cumulative attributes down all the paths. And when it comes back, you don't want to add them together because you will have duplicated your accumulation. So when you see ReturnDiv equals 1, you know something's coming back and you can't just add your inflows together or you'll duplicately count and there's no way to know how much. You know, there may have been a divergence and then another divergence and another one off of that. So when you're sitting there, you say, there's no way for me to know what the accumulation is here. I navigate upstream and I add up all the values. It's the only way to solve that problem. So here we have, here's a little example of this. We have a divergence right here. So we go down a green path, and we go down this path, and things proceed and proceed, and they get down here, and all of a sudden we're coming back together. And that's where ReturnDiv becomes 1. And it says, something's just come back in that left you upstream, So beware. Don't add everything together. And that is the end of part 2 of value-added attributes. Are there any questions?